Hello everybody. So in this video we're going to discuss a very important point that I personally see that it's very important to discuss before we go through the next parts in the chapter. This is something that is more related to mathematics, but it's very relevant here because this is something that we used to do a lot in this course and in other courses in physics, mainly for those who have taken physics courses before. So this is about the question that you see on the screen now is why do we use differential equations? So this is something I think we don't learn in math courses because most of the math courses are taught by mathematicians, and they're more interested in math than in the applications of math. And this is like something that we as engineers are more interested in, which is the applications, and why we do these kind of write the equations in this form. So to understand or to get the answer, I will clarify this in two simple examples. The example that we see here is a surface that is uniform surface and that is exposed to a uniform force. So the force is equal on all the points, and in order to calculate the pressure, we can use a very simple equation, which is pressure equals force over area. And this equation is a valid equation, and we can use this equation. And if we have a tool that can measure the pressure at each point here, you can find that the value of the pressure that we measure is going to be the same as the value that we calculate here by dividing the force over the whole area. And we were able to describe this system using this equation because the system is categorized under a category of systems that we call lumped parameter system. We mean by lumped parameter system is a system that the parameter is doesn't change through the system. So like in this case, through this area, the force is the same, so it's called a lumped parameter system. There is no change in the force from one point to another. So in this case, the simple algebraic equation is enough to describe the system efficiently and to give a good explanation of how the pressure or the value of the pressure. Okay. So this is a very simple case, and of course the equation is going to be simple. So we can use a simple algebraic equation to describe this system. The second system that we are going to discuss is a very similar system with one important difference, is that the force is not constant. It's not homogeneous over the whole area. So you see here the length of the arrow represents the value of the force. So here we have small force, and then it gets larger, then decreases, then increases and decreases. So the pressure at each point is different from the other points, because the force here is different from here. So of course the pressure here is much higher than the pressure here. So in this case, the equation that we used before is not going to be valid in this case. Okay. So we need to think of a way to write an equation that describes this system. And by the way, writing equations is very important because the equation that you write can express the system and can model the system. So you can use this equation to design systems and do other things without the need of doing the actual testing yourself. Okay. So you need to make sure that the equation that you write is a valid equation, or that expresses or represents the system in a very good way. So in order to do this, we do something that, or to express the system using an equation, we do something that we used to do before, and I believe many of the those who are watching this video now are or don't know why we used to do this. What we do is so you need to have a point clear in mind that the only system that we can describe using an equation is a lumped parameter system. This has to be clear. You cannot express a system with an equation unless it's a lumped parameter system. So for a case like this, we don't have a lump parameter system. So we can have a tweak to use a lumped parameter system equation for this distributed parameter system. And this tweak is that we take a very small part of this area. This is what we call the differential area. Okay, so when we take this differential area, we can consider that this area is very small, so that the force over this area is homogeneous. Okay, so let's say you are taking 1 micron square, for example, of this area. So this is a very small area that there is no chance that the force is going to change in this small area. So you can consider that the area, the differential area dA, and the differential force dF acting on this area, that this system is a lumped parameter system. So now we can do the same thing that we did last time, but not for the whole system, but just for this differential part. So now when you write the equation, you would see that the dP equals dF by dA, or F dA, depending on how you write the equation. And now without even thinking of the equation as algebraic or differential, the equation now came to be a differential equation. Okay, so the equation is a differential equation because the nature of the system forced us to deal with it in a differential way. We cannot use the lumped parameter system equation, which is an algebraic equation, to describe the system. So we had to take a very small part of it, consider it as a lumped parameter system, and write an equation based on the differential force and the differential area. Okay, so now we have an equation that describes our system in a good way, and it takes a very small part. So the equation is valid for this differential force or differential area. So till now, this is a very good point. Now, so now we understand or answered one part of the question, which is why do we use differential equations? Because this is the only way to describe the system. For any distributed parameter system, the only way to describe it is the differential equation. And this is why you would take a differential part of the of area, or part of or differential volume, or differential time, for other things that we used to describe mathematically before, because this is the only way to do this. So now we ended up with an equation, but at the end of the day, the equation is not needed just to have an equation. The equation is needed to use it for design, for substitution. So we will face another issue now, that we cannot substitute in this equation directly. Comparing to this equation, I can directly substitute the force here, the area here, and calculate the pressure. Algebraic equations are very simple. You just put numbers and you calculate. But for the differential equation, for differential equation, it's a different story. We cannot substitute in this equation directly. And beside this, the equation that we have describes a very small part of it, a differential part of the area. It's not the whole area. It doesn't describe the whole system. It describes a very small part of the system. So this equation cannot be used as it is. So in order to use this equation, we need to have a tool that allows us to convert this equation from a differential equation into an algebraic equation, and this tool is the integration. So this is why we do integration. I know integration is not a fun thing to do, but we have to do this because this is the only way to convert, or the only tool that we have to convert this differential equation from a differential form into an algebraic form. And this is why we spend a lot of time in math classes and in calculus classes doing these integrations and differentiations, because we need to master this or master this tool and know how to do this integration, or convert this differential equation that we cannot use as it is to an algebraic equation that we can use, or to do other ways of integration, like graphical integration, for example. If you do the trapezoidal rule or Simpson rule for doing the integrations, these are tools that are needed to make this equation useful. Otherwise, we are not going to make any use of this equation in its differential form. So I hope that this discussion that I made here made it clear. I personally didn't have the chance to learn this thing when I was a student, and I always had this question when we did any derivation. Why do we start with a differential equation? Why do we start with a differential volume or a differential area, and go through this hassle of doing integrations and doing all these things? But I hope now I made this point clear before we go through the derivation of the pressure at a point that we're going to do in the next video. So this will make things more clear for you, and will make it more logical when you, or you'll even expect that any derivation or a specific derivation that you're going to go through, that you have to start with a differential element, or you can go with the algebraic equation, or a general simple equation. This the sense of this will depend on your understanding of this point that I discussed in this video. So I hope I made it clear, and I hope this is useful. This is the end of this video. In the next video, we are going to go through the derivation of the pressure at a point in a static fluid. So I'll see you then, inshallah. Goodbye.